All right, let's get at this problem here. So, hollow metal sphere has 6 and 10 centimeter inner and outer radius. Surface charge density is a minus 100 nanocoulombs per square meter, and the outside is a plus 100. So, we want to do the strength and direction, electric field at various points from the center. So, let's get at the computations here. So first, just to get some things out of the way, is we need to first figure out what the charge inside is. And so if we just take that first one, the inner one, 100 nanocoulombs per square meter, and the charge on the inside will be the charge density times the area, surface area, of that sphere, which is 4 pi, and then the radius squared, so 0.06 meters squared. So trusting that you know the area density times the area will give you the actual charge. And so this computes out to a negative 4.524 nanocoulombs. So we have that. It is worth noting that the electric field is going to be perpendicular to that surface area at all points. We would expect that with a spherical distribution and the way we understand fields. Now, one thing that's perhaps not perfectly obvious, but is worth stating here, this charge is caused by polarization, which means that there must be a plus 4.524 nanocoulomb charge at the center. So we have to go with that, it must be that way. So now you know, and we can get at solving the problem. So let's take our first spot here where R is the 4 centimeter mark. And so all of these we can start with the statement of Gauss's law, where the electric flux would be the surface integral of the field vector dotted with the area vector. Remember, that's how we came to understand flux in the first place. And that's just going to work out to the field times the area. And according to Gauss's law, charge inside for epsilon naught. You could just think of flux as charge per unit, this fundamental constant, or the fundamental constant is the charge per unit flux. That's probably a more natural way to go. But of course, this means that my electric field, from a theoretical or a computational standpoint, would be the area, or the charge divided by area epsilon naught. All right, so if we plug and chug those numbers, the area that's given, 4 pi r squared, the epsilon naught, etc., we come up with 2.54 times 10 to the fourth newtons per coulomb, if you just plug and chug all of those values in. What about at 8 centimeters? Well, at 8 centimeters, if we pay close attention here, we're now on the inside of the conductor, and electric field is just zero for a conductor in electrostatic equilibrium. Just can't be any other way. And we'll be reinforcing that over and over again as we move forward, especially into circuits. All right, so we have that. What about at 12 centimeters? Well, Q outside. So remember at 12 centimeters, we are out here on that Gaussian surface. So we're just past the surface of the actual metal sphere. And the Q outside is going to have to be all the charge that's out there that we were told was out there. So that's going to be a plus 100 nanocoulombs per square meter. Also going to be by its surface area, but the surface area we're dealing with there is at 10 centimeters or 0.1 meters squared. And so on the outside, we have 1.257 times 10 to the minus 8 coulombs of charge out there. And so our flux equation, we can go straight to the EA equals Qn per epsilon naught, all right? But Qn, what is that going to be? We need to know what the Q on the inside is. And this is the Q enclosed relative to Gauss's law. So we need to stop, drop, roll, and figure that out. So the Qn, this is the thing that's relative to the Gaussian surface. That's going to be this outside charge, everything that's on the inside of the Gaussian surface, plus the charge that's on the inside of the sphere, not to be confused with the Qn for Gauss's law, and then the Q at the center, the charge at the center, the thing that's polarizing the inside sphere charges. All of that's going to be what our Qn is. And so hopefully you recognize that these two charges here, they're going to wipe each other out. So the Q inside and the Q center, all those just wipe out. There's nothing there. So we're really just, what we just computed ends up being, luckily for us, the answer, at least for what Q sub n, the Gaussian, inside the Gaussian sphere, part is. And so 1.257 times 10 to the minus 8 coulombs over that area. Epsilon naught in the area, of course, would be 4 pi times the 0.12 meters squared, 12 centimeters. And you crunch all of that, and you get 7.86 times 10 to the third newtons per coulomb. So that's applying Gaussian reasoning and computations to a relatively simple spherical distribution of charges. So let's continue on that. We should note that positive test charge Q, center of a hollow shell. The shell has negligible thickness and a net charge of minus 2Q, and we want to get a number of things: electric field inside the sphere, outside of it, etc. We should note that the electric field is also going to be perpendicular to the area at all points on the surface. And this will be common with the way that we're approaching these Gaussian things. So let's look at part A for inside the sphere, for r less than big R. So again, if we can formally state Gauss's law as such, and that means that when we do that surface integral, we're going to get EA again, electric field times that area, and we know that flux is equal to the charge inside of the Gaussian sphere over epsilon naught. Draw that naught a little bit better. And so what does this mean? Well, if I solve this for A, I get this thing that we keep seeing over and over again, Qn A epsilon naught. And the charge on the inside of that first Gaussian surface is just a plus little q per r squared, and then there's a 1 over 4 pi epsilon naught. Let me redo that. Got a little ahead of myself. So I could write this a number of ways, but I know that my area is going to provide me with a 4 pi, and then there's going to be that r squared that comes with the area. And then there's an epsilon naught in that regard there, and then we have this plus q. So this is sort of our classic, this is Coulomb's law again, and if in a vector form, if E became a vector, it'd be because it was pointing somewhere, such as r hat in the direction along the where the action happens, and this is going to be, in our case, outward, given that it's a plus charge, all of the fields pushing out for that part of the puzzle. All right, so that's part A. Part B, of course, is going to be a similar situation since we're dealing with the spherical distribution, and so we can just go straight to the, no need to rewrite Gauss's law again. And so this means, again, my E, my electric field, Q per A epsilon naught. But what's the Q on the inside? Okay, so the Q on the inside of this Gaussian surface, and that's the trick to remember, is going to be a minus 2Q. That's what is out here, plus the same Q that we were dealing with a minute ago. So now I can finish that work here. And so we're going to get a minus Q per A epsilon naught, which means we'll have a minus 1 over 4 pi epsilon naught Q per r squared. And again, in vector form, you would have that going for us. And since it's a negative sign, this one's going to be inward. And that was because that outer shell of charge had double the magnitude but opposite the direction. So we have completed that problem. Moving on to the next one. Let's see here. Part A. Or we're just going to make a part A here. We're going to consider the r, little r less than big R. So this region right here. So the Q on the inside is 0. There's no charge there. And so that implies that the flux, electric flux is 0, which implies the electric field is 0. So that one's easy. We don't even need to compute anything. R greater than R. Well, that's going to be this shell out here. Well, obviously we're going to have some flux due to that. So again, our electric flux, we'll skip the integral. It's going to be electric field times the area, which we know is the charge inside per epsilon naught. And this means that my electric field, one more time, surface area epsilon naught. And we just get the classic Coulomb's law thing again. And that's it. So it's kind of a simple demo problem, nothing outrageous to consider there. But this next one, a little bit more involved. But we're going to use all of those ideas that we've already seen. I do need to make a correction, though. This R less than B, this should be A less than R less than B. So a little typo in the making of this show. So let's deal with part A here. The part where R is less than or equal to A. Well, part A involves a number of parts. This one, this one, this one, and this one. So we'll have the R less than or equal to A part of part A. Again, electric flux, it's going to be Qn per epsilon naught. And we can skip the integral because it's just another sphere. If we had some other shape, then it might be worth writing out the entire integral. And there's a minus Q charge at the center there. And so we know that, or we can rightly deduce that, of course, this is also equal to EA, but it's going to be a minus EA because of the charge that we're dealing with. I could put the minus Q on the minus on the Q if I wanted, but we'll just put it here for this right here. So we're going to have a minus E times 4 pi r squared because it's a surface area thing again. Now, the Q, we're dealing with, this is a ball. Okay, so we're dealing with a volume. So we're dealing with a volume charge density. All right, so Q, let's just sort of, Q would have to be a volume charge density times the volume. Well, that would mean that we have this volume charge density times 4 pi over 3 r cubed. And so that means when we go to put Q, our enclosed, or the charge on the inside, this is what we need to be dealing with. So continuing over here, this means that my electric field, okay, is going to end up being a minus Qn per area epsilon naught. And so my charge is going to be this minus density, the 4 pi over 3 r cubed. The area is 4 pi r squared. And then we have our epsilon naught. So this means that my electric field, at the end of all of that, will be this charge density, volumetric charge density at some distance, and this 3 epsilon naught, right? So there's our electric field for that region where R is less than or equal to A, which I inadvertently capitalized. Didn't mean to do that. All right. So there's our R less than or equal to A, but we're not done, okay? Because we need to consider what this surface charge density is. So one more little twist in the puzzle. So here, in this case, our volumetric charge density would equal some amount of charge, it's a minus Q in this case, per the volume. So 4 pi cubed, and that's going to be at this A cubed, because A, this radius here, that's what the A is. All right, so that little link there is our A. And so that's why that comes in this way. So now, all of this would have to come up and be part of that mess of things. Or actually, we could slam that over into there. So let's do that. So my electric field would end up being, and so let's just kind of look here. We're going to lose some 4 pi going on there. 3 will stick around. R is going to drop down, but so we can just write in here minus Q. Well, let's do this. We'll have our minus sign, drop that out from the front. We're going to have 1 over 4 pi epsilon naught, and then that Q, the R stays on top, and the A cubed. So our electric field in this region would have this property, and then as a vector with that direction there. So we obtain this interesting twist on Coulomb's law of the field here, and instead of an r squared in the denominator, we have this other thing. So just we get this because we had to go through charge density manipulations and whatnot. All right. What about the region A less than R less than B? Well, once again, we're going to have a negative EA, direction of things going. This is going to be a minus Q per epsilon naught. And so this means that our electric field is just going to give us that Coulomb's law thing back. 4 pi epsilon naught Q per R squared. And if it were a vector, we would have that property going for it. So again, the A between R and B, this is, let's see, yes, so we're in this B circle versus that A circle. So that read between those two Gaussian surfaces. All right. What about the B less than or equal to R less than or equal to C? This is inside of, that's here. So it's inside of the actual metal. And once again, E is 0 when you're in a conductor in static equilibrium. So we've seen that a couple times now. So I'm going to bank on that. And then R greater than C. What is that going to give for us? Well, let's get to the Q on the inside of the Gaussian surface. All right, so this is taking us all the way out to this outer region here. And Qn, what's it going to be? Well, it's going to be the sum of all the charges on the inside. And on the inside, if you look up here, don't even have to figure it out where it is in the picture. I have to include everything. So I have a minus Q plus 2Q, which is just a minus Q. I'm sorry, plus Q. And once again, EA, Qn per epsilon naught implies that our field is going to be 1 over 4 pi epsilon naught. And we have the Q, and then, whoops, it's not equal to, that's times. Then that R squared part of the area. So once again, Coulomb's law keeps sticking its nose in our Gaussian business, but that's unsurprising since they're functionally equivalent things. So that distribution. We're going to skip this problem because I want to, and I'm going to skip a bunch of problems because then that gives me test material. Hint. All right, this problem. Let's get our mind around this one here. So an infinite slab. I just want to pause. And when you have an infinite slab, an infinite line, you get some interesting properties with the electric field. You get a lot of uniformity past the surface of it. And so we'll unpack that a little bit as we go. So let's get at it here. So let's deal with part A, the z less than z naught. All right. So formally, if we were to pay attention to the surface integral, we would notice that it has some parts. I would want to integrate the top EDA. I would want to integrate the bottom EDA, so we're no longer doing a simple spherical surface. We're doing things that have different dimensions. I can't integrate it all at once. I'd have to bust it into its pieces parts. And of course, this is Qn per epsilon naught in there. All right, so some things to notice is that right here, this goes to 0, and the reason for that is the field is perpendicular to the area. So you can just dump that one out right there. We should also notice that since we're dealing with a volume, the charge inside could be the surface charge density times that volume. And the volume is going to be 2z, which is our dimension over here. And then it's going to be times the area. All right, so because we're talking about a cylinder. So our charge could be written as the charge density, the volumetric charge density times 2Za. Just running those things out there. So little stuff in there. Also, these two things are the same. They're both EA, so they would add up to 2EA. So just some easy peasy stuff to do there. And so we'll work at that here. So our Qn per epsilon naught, okay, so we'd have our rho 2Za per epsilon naught. That would need to equal this 2Ea right here. Well, that means that my electric field would boil down, if I pay attention to those last two things in equality, I would have that volumetric charge density times that dimension z, length of the cylinder, per epsilon naught. So this just means that my field is going to increase linearly with distance from the center. All right, so we could make a note of that. E increases linearly with distance. Let's just pay attention to that little computational part of the puzzle here. So, part A down. What about z greater than z naught? Again, my charge is going to be equal to rho times 2Za. Nothing unusual here. And let's see. My Q on the inside of the Gaussian surface, just like before, rho 2Z naught A. I guess I got to put my naught here since we're dealing with a different Gaussian sphere here, per epsilon naught. And here, it's the same deal. We have these two things going on and none of that. So we're back to 2Ea. Nothing's really changed in that regard. And so we end up getting E is the same thing except it's relative to Z naught for epsilon naught. Two identical things here. Now part C wants us to graph it. So we'll make that the Z dimension. Told you this was easy. Get it? E, Z. All right. So at some rho Z naught per epsilon naught, and then we would have a Z naught, a 2 Z naught, and a 3 Z naught. And so we're told that it increases linearly with distance from the center, and then it's going to go flat out here. And the reason for that is the field strength outside E is constant outside the slab. Now that may not be obvious to you, but the reason here is because it's an infinite slab. So every part along infinite directions is bubbling over, so to speak, to every other part. And so when you get past, you have a constant field strength outside of the slab. Gonna skip that one because it was like the other one I skipped. And I'm gonna skip that one too because it's just a lot like the one we just did. Again, test questions. You have the paper with no slash circles on it. So I trust that you can check into that at your convenience. I do want to point out that we have a line, a linear charge density running down the center, okay? And then we also have a linear charge density along the cylinder, okay? Out there, just the pictures are kind of small, so you got to read that. So we want electric field strength inside, outside the cylinder. So let's do some stuff here. But before we do some stuff, let's make some observations. So the symmetry of situation here implies that the only possible shape of the electric field is inward or outward. Okay, so charges in or on the surface of these this wire, they can only point in or out. And the reason for that is those field lines can't cross each other. So if they're all lined up, they all have to point outward, inward or outward radially. So we get no other option for that. And so we use a Gaussian cylinder because it's already a cylinder. And just know that a long, thin wire equates to an infinitely long thin wire. So that means infinitely long. That's the interpretation that you should obtain from those sorts of statements. All right, so let's talk about part A, where R is less than big R. Our flux, our electric flux, is going to be, since it's a simple radially outward, this is equivalent to a sphere or a slice of a sphere, so we don't have to worry about the surface integral because it's just going to boil down to that. But at the top and the bottom, all right, so I am going to write out these surface integrals just for clarity's sake. You know, we would have a top EDA, we would have a bottom EDA, and we would have the sides. That's what the single surface integral would work out to be for this. And we're talking about linear charge density of the thin wire. R less than R is on the inside. And so that's that uh, linear charge density times the length of the wire per epsilon naught. All right. But this is 0 and that is 0. Why are the top and bottoms 0? Well, and this is going to be an EA. They're 0 because it's infinitely long. So compared to the rest of the distribution, they're just not even there. They don't contribute anything that changes the overall uniform field. So that's why we dump them out and remain unconcerned with their progress. So EA, I'm going to kill this color of it and just go, EA is going to be our lambda L per epsilon naught, which means that the electric field, come back over here, will, the area 2 pi r times the length. Now, what is that? Remember, if I take a cylinder and I slice it, okay, then it works out into a rectangle. And we had, this would be the 2 pi r, and that would be the length of it. All right, so just so that's where that's coming from. And this is equal to our lambda L per epsilon naught. So all of that boils down to an electric field that would have, all the constants would be lambda per 2 pi epsilon naught, and then we would have 1 over r. And again, if we were to put a vector on it, that's what it would be. So we get something that's basically, it's not an inverse square electric field. It's just a inverse to the distance, and not a 4 pi. So it's not Coulomb's constant, it's half a Coulomb's constant. And the charge densities in there, etc. So it's a little bit different. Coulomb's law takes a different structure when the geometry departs from the standard spherical consideration, which is the simplest. And that's why we think, just kind of stepping back a minute, that's why we think atoms and whatnot are spherical, because of the way the fields behave. So, all right. For part B, we can just go straight to this thing, which is going to be equal to EA. But what is Qn? Well, Qn is going to be the charge along the line of charge, this part here, plus all the charge that's out on the cylinder. All right, and so that's going to be a lambda L plus a 2 lambda L per epsilon naught. And this has to equal my EA, and my A is a 2 pi RL. All right, so again, we can, well, we might as well do some of the math here. So I'm going to get a 3 lambda L per epsilon naught equals 2 pi R EL, which means my electric field will simply be a 3 lambda per 2 pi epsilon naught times the 1 over R. And again, as a vector, it would simply have that direction for it. So that's the long and short on that one. Okay, a very long uniformly charged cylinder, that means infinitely long. So those little clues in the reading tell you things like that. We saw that at the very large slab of cylinder, also meant an infinite plane, basically. So let's get at this problem. So part A involves when that inner radius is bigger than some larger radius. outside of it, or the of the surface itself. And once again, when we do this surface integral, we've seen this before for the last cylinder, we would have some sort of field popping out to the left as well as the right, or we would need to account for it if it's there and if it matters, which it doesn't in this case because it's infinitely long. But the wall, because everything's moving radially outward just like it was in the last time when it was tipped up vertically, okay? And all of that, according to Gauss's law, would be the Q inside of the Gaussian surface per epsilon naught. And this is 0, that's 0, this is going to be EA again. So again, we have a relatively simple puzzle here. And so if EA equals this Q in here, so we've seen this before, we're going to have our electric field would be Q in area epsilon naught. And so let's get at plugging and chugging things here. So we have a linear charge density, lambda. And so the total charge would be lambda L, the charge density times the length. The area is going to be a 2 pi RL, okay? So, because we're dealing with a cylinder, and then the epsilon naught. And so, in the end, we'll get, all of our constants, 2 pi epsilon naught, and we'll have our 1 over r here. And so as a vector, once again, we have this version of things. So it's sort of a repeat of the last one. Nothing really new under that sun. So let's deal with r less than or equal to r. So once again, EA is going to be our Q sub n epsilon naught. So our electric field, Qn per area epsilon naught. So let's bust this out. So there's a lot going on here. So inside of the volume, we're dealing with a volumetric charge density, and the volume of a cylinder would be pi r squared L. The area, the surface area, is just going to be 2 pi little r L epsilon naught. Now let's deal with this volume charge density, but we can deal with volume charge density in terms of the linear charge density. So little tangent here. Volume density in terms of linear density. That's what we're going to work on here. So charge has to equal charge. All right, so we're just going to set up an identity here. So linear charge density times we'll just use D for the cylinder length, would have to equal the volume charge density times the cylinder volume in those same terms. So really all I did there is I put linear density and volumetric charge density into an equivalence relationship based on the thing that converts that density into charge. So the D converts lambda into charge, pi r squared D converts rho into charge, and charge has to equal charge. Well, this gets us to our volume charge density in terms of lambda would just be this, lambda per pi r squared. So that what that lets us do is take our E from above here, so we're going to pop things down into here. Now that means I can put that rho lambda per pi r squared And then I can take what I had above there, pi r squared L per 2 pi little rl epsilon naught. And so that means that E will work out to be 1 over 2 pi epsilon naught lambda little r per r squared. And once again, as a vector, we could put those things on it and we're in business. Finally, part C. What about when r equals r? Well, now we're just going to replace things here. So the E when r equals r would just be 1 over 2 pi epsilon naught. And instead of lambda little r, it would be lambda big R per r squared, which means 1 over 2 pi epsilon naught lambda per r. And once again, as a vector, we would just pop that on here. So let me kind of section things off here to keep it all separate. And that would be our answer in that case. So easy peasy, if you will, problem there. So that's problem 10. Now, problem 11. Let's move on here. Just 2 more to do. The rest are test material, most of the rest. All right, so looking at this one here, another set of spherical shells, and we have Gaussian surfaces inside and outside of the actual material, and then one on the inside of the material. So we've done this kind of problem before. So let's do some setup here. So let's talk about the R greater than R out, part A. And so once again, spherical stuff. So Qn for epsilon naught equals EA. This is sort of old news by now, at least I hope it is. And so the area is going to be another 4 pi r squared. So we shouldn't be surprised that when we go through all of this business that we get 1 over 4 pi epsilon naught and just our Q over r squared. In fact, we've done this I think a couple times already. As a vector, it would have that property. So easy, not a lot to deal with there. What about r less than or equal to the radius n? Well, this area here that we're talking about, that's inside, there's nothing, there's no charge there. And so if there's no charge there, right, so if Q equals 0, then the field due to that equals 0. So that was easy. What about when little r is sandwiched in between the r in and r out? So once again, EA equals Qn per epsilon naught. They just state in Gauss's law, which of course is the same thing we keep seeing. Charge per area epsilon naught. But what's Qn? Well, the charge that's on the inside for this is a volume issue. So since it's within a volume, we use volume charge density, so that times volume will give us that charge. Okay, and so let's deal with the volume. Well, 4/3 pi times what? Well, you have an inner and outer volume, and so depending on where you're at, you're going to have an r cubed minus an r inner volume cube. So that's, where am I at here's that inner big R, and then R is going to be extending out through this area. So your volume at any given location, R between the in and the out, that's going to be your volume at that location relative to your charge density. So now we have a statement for the charge on the inside of your Gaussian surface, or we have the volume for that, but we haven't defined the charge density, the volumetric charge density. And so that is our next step. And so what I want to do is kind of change colors here in a second to deal with that. So I'm going to write what we have. We have 4 pi over 3, and what we're going to have in the numerator is what we just wrote, this r cubed minus big R sub n cubed. But now I'm gonna change up colors here. So the volume charge density part, well, it's going to be the total charge there per what? Per a spherical volume again, which is going to be 4 pi over 3. But what's it going to be? It's going to be the large radii, the outer one cube minus the inner one cube. That's going to be our, in blue there, our volume charge density for the material part of this physical situation. All right, so there's a lot of stuff going on there. And so in the end, Q inside of the Gaussian surface, wherever little r is at, will simply be the total charge, and we're going to have these ratios. As shown here. So that's going to be the total charge on the inside. So the thing that's different here is the geometry, and the areas we're paying attention to require us to have a more complicated expression for charge. And we'll get what we get from that. So therefore, and this little triple dot thing is a math shorthand for therefore, Qn per area epsilon naught will end up being well, we're going to have 1 over 4 pi epsilon naught. Now I'm leaving the r squared to a different spot. That q is going to come in here, and then we're going to be left with all of this mess with ratios of cubed radii. So just to be clear, I guess, area was this 4 pi r squared business, just so we're clear on that. And if this is a vector, then as usual, we would have that going for us in that regard. So that's our expression for the electric field when R is sandwiched between somewhere inside of the actual material itself. All right. Last part here. Skip the graph. Well, for one, if R equals Rn, then the electric field is going to be 0, because up here you would have a 0 on top. So that's easy. If R equals R out, well, then that means you have an R out cubed here, and you have a fancy form of 1. You have something over itself. And so that means the electric field would just be back to the Coulomb version that we're accustomed to. We would just have, oops, I keep putting equal sign there. All right, a Q per R squared. So that's it for that problem there. And number 12, the last one before we skip everything and make it test material. This is a good one. a practical one, at least theoretically for physics. So the Rutherford atom, the discovery of the nucleus, would have some point charge. The nucleus would be a plus Z, whatever the atomic number is, times that number of uh, fundamental charge units. And so we want to show that the electric field is somehow equal to that. So let's take a swing. So for inside the atom, which is our R less than R situation, once again, the charge inside, it would be volume charge density times volume, and again, our 4 pi thirds R cubed, and that's going to be plus whatever is at the middle. Okay, so we have whatever charge enclosed by little r, wherever it's at, plus the charge that's in the middle. And so you do all of this um, uh, math here. So first, let's deal with this. What's rho going to be? All right, so the volume charge density would have to be minus ZE. So we're out here at the outer edge per 4 pi thirds big R cubed. So this is our volume charge density for the whole stinking atom, all right? And then we'll still have the 4 pi thirds with the little r cubed plus ZE. Well, that means that at the end of the game here, at least for determining what Qn is, we're just going to have ZE minus ZE and this ratio of cubed whatchamacallits. And that would boil down more simply to ZE times 1 minus that ratio. Okay, so now we have as simple a definition of the charge on the inside of our Gaussian surface as is possible. And so once again, we'll skip all of the formal writing of Gauss's law. We'll just boil it down to the field thing here. And of course, we're going to have our ZE then times all of this stuff here, and then the area epsilon naught. And so we have 4 pi r squared epsilon naught. And so at the end of all of this, we could simplify this to the electric field is going to be ZE per 4 pi epsilon naught, and then we would have 1 over r squared minus r over r cubed. I trust you can crunch those numbers around and get that answer there, but so we've shown that works. Okay. Part B, what is E at the surface of the atom, or when little r equals big R? Well, that would just mean, so we're just going to take this and let little r equal big R. And so we'll get E will be all of this constant stuff out in front. And we'll have 1 over big R squared minus r over r cubed. Well, that's just 0, because this r over r cubed is a 1 over r squared. So we get nothing at the surface, which we would expect for an electrically neutral atom. So electrically neutral atom, equals 0. All right, so part C, our computation here. So at R equals big R over 2, we want to know the field strength there. So let's see. The electric field on the inside, let's see, we'll have an atomic number of 92. E is 1.602 times 10 to the minus 19 coulombs. We could divide by the 4 pi epsilon naught, or we could just multiply by K, which is 9 times 10 to the ninth. What are the units? Coulomb squared per Newton meter squared. All of that. And then we would have 1 over, and we're doing it at half that big R, when little r is half big R. So that's getting squared, minus that number not getting squared, but over the big R cubed, which is 0.1 meter cubed. And so we do all of that, and we're going to get 4.6 times 10 to the 13 newtons per coulomb. And that, my friends, is a wrap.